All right, so last time we talked about the structure of atoms. What's really important to remember about atoms is that they are electrically neutral. The reason why they have no net electrical charge is because the positive charge of the protons is canceled out by the negative charge of the electrons. And the only way that that happens is when you have the same number of protons as electrons. Well, sometimes there's situations where you have a particle. I don't want to call it an atom. Sometimes people use the term atom here. I'm going to call it a particle that has an electrical charge, and these are called ions. So an ion is kind of, if you want to think of it this way, even though I don't like this word, an atom with a charge. Now, it's not really an atom, but we'll call it a particle that has a charge. Now, there's two types of ions. You have positive ions and you have negative ions. This is really, really, really important to know why these ions have either a positive or negative charge. So in order to have a charge, there must be a different number of protons as electrons. Again, if it's the same number, then there's no charge. But if you have, say, more of one than the other, then you're going to have a particle that has a net electrical charge. So let's start with positive ions. These ions form when a neutral atom loses one or more electrons. So very important to understand that atoms can somewhat easily gain and lose electrons, but they cannot gain and lose protons. So again, remember, protons determines what an atom, or in this case an ion, is. So that never changes, at least not until we get to nuclear chemistry later on in the year. So has to do with removal of, in this case, electrons, removal of electrons to form positive ions. So here are some examples. When we write the symbol for an ion, we include its charge as a superscript. So for example, sodium forms an ion with a +1 charge. If it's the number 1, we don't have to write 1, so we just put plus, so that has a +1 charge. Calcium forms an ion with a +2 charge. Now think about how this happens. How can sodium form an ion with a +1 charge? That must mean that sodium, the neutral atom, loses 1 electron. And so then the particle that you end up with still has 11 protons because it's still sodium, but it must have 10 electrons. 11 positives, 10 negatives for a net charge of +1. In the case of calcium, to form a +2 ion, think about what happens to the neutral atom. So calcium has 20 protons and electrons. This ion, specifically this charge, is telling us that the ion of calcium has 2 more protons than electrons. Well, if it has 20 protons, it has to be 20 because it's calcium, 20 protons, this ion then must have 18 electrons. Here's another example. Silver forms an ion with a +1 charge. Lead forms an ion that has a +4 charge. So there's all these substances that can form these positive ions known as cations. So again, what's important, atom, when it loses electrons, 1 or more, will form a positive ion known as a cation. Now, these ions don't just get ripped off and they don't go into space. They go somewhere. So where in the heck do they go? Well, perhaps they go to another atom. We'll talk about this transfer of electrons that occurs when we talk about chemical bonds. So negative ions form when a neutral atom gains, again, electrons. 1 or more electrons. Always electrons. So let me show you some examples of these negative ions. These negative ions are known as anions. Fluorine forms an ion with a -1 charge. How does it do that? Well, the neutral atom fluorine has 9 protons and 9 electrons. And it can gain 1 more electron to form this ion. So this ion has still 9 protons, it's still fluorine, but this -1 charge tells us that it must have 10 electrons. Therefore, we got 9 positives, 10 negatives for a net charge of -1. Now, if you recall from the last lesson, I said What is something that has 6 protons? That's carbon. Something has 8 protons. What is that? That's oxygen. If something has 10 electrons, what is that? Now you might be tempted to say neon. Well, yes, if it's a neutral atom, but I've already given you 2 examples of ions that also have 10 electrons. Namely, Na+, a sodium ion, has 10 electrons. So does F-. So the point I was trying to make is we can't tell what something is just by looking at the number of electrons, because in this case we see that many things can have 10 electrons. Here's another example of an anion. Sulfur forms an ion with a -2 charge. So how many protons and how many electrons does this ion have? Well, it's sulfur, so it has 16 protons. Has a -2 charge. That means there are 2 more electrons than protons. Remember that. -2. More negatives than positives. 2 more electrons than protons, so it must have 18 electrons. Here's another one. Phosphorus forms an ion with a -3 charge. This ion has 15 protons, it's phosphorus, and 3 more electrons than protons, that must be 18 electrons, just like the ion of sulfur. They both have 18 electrons. Usually we'll call this the charge of the ion, but you may see also the word valence, so that's another word for charge. For some substances, we can predict the charges of their ions. We can predict how many electrons they will gain to form an anion, or how many electrons they will lose to form a cation. Here's how it works. It says many atoms ionize. So the word ionize means to form an ion, so as to have the same number of electrons as the atoms of the elements in the far right column of the periodic table. Make a note. The elements all the way to the right, this is group 18, are called the noble gases. Now, what is so special about the noble gases? Why are they so noble? Well, the noble gases are special because they are what we call stable. They don't want to gain electrons. They don't want to lose electrons. They're happy with what they have. And so that is why the noble gases are inert for the most part, meaning they don't undergo chemical reactions because they already have a stable arrangement of electrons. So other atoms can achieve stability by gaining or losing electrons to be like what I call like a noble gas. Now, it's not that they're turning into a noble gas. Remember, the number of protons doesn't change. So when you hear me say like a noble gas, that means they have the same number of electrons as a noble gas. Here's how it works. Find the zigzag on your periodic table. So it's towards the right side of the periodic table. We're going to reference that zigzag. So that zigzag kind of separates the periodic table into different types of elements. Atoms to the left of the zigzag, first of all, for the most part, are metals. And metals like to lose electrons to form cations. So everything to the left of the zigzag is going to lose 1 or more electrons to form an ion. And again, not everything wants to be like a noble gas, by the way. So if you take something, say, in the middle of the periodic table, like iron, iron has 26 electrons. It's not going to lose 8 electrons to be like argon. That is impossible. So atoms, when we talk about gaining or losing electrons, usually it's no more than 3. Sometimes it's 4 electrons gained or lost, but usually it's 3 or less. Again, there are exceptions. Atoms to the right side of the zigzag, except for the noble gases, tend to gain electrons. Those elements to the right of the zigzag are nonmetals. Nonmetal atoms like to gain electrons to form anions. So let's take a look at some examples. And we're going to get to this in the notes in a little bit officially, but I want to mention this now. So what I'm going to do is I'm going to write something called ionization equations. And so an ionization equation shows how a neutral atom forms an ion. So let's do that. Find magnesium on the periodic table. Next, how many protons and electrons does magnesium have? Pause the video if you need to answer that question. Magnesium has 12 protons and 12 electrons. Now, here's how it works. Number 4, going back to that. Atoms want to gain or lose electrons to be like the noble gas closest to them in number. Not necessarily the one that's in the same row, but closest to them in number. Now, which noble gas is closest in number to magnesium? And again, pause if you need to find this. That answer is neon. Now, how many electrons does neon have? Well, neon has 10 electrons. Well, guess what? Magnesium wants to be like neon. How can magnesium become like neon? It can do so by losing 2 electrons. So let's write the equation showing how this happens. So here's the thing. Any ionization equation you write, there's 2 things that we always see in every ionization equation. First, the neutral atom goes on the left side of the equation. Next, the ion, the symbol of the ion, goes on the right side, always, no matter what. And then the electrons, we're going to show electrons. Sometimes they're on the left side, sometimes they're on the right, depending if the atom gains or loses electrons. So in the case of magnesium, it likes to lose electrons, 2 of them to be exact. And when magnesium loses 2 electrons, the ion that forms will have how many protons? That's right, it'll have still 12 protons. How many electrons will it have? It will have 10 electrons. 12 positives, 10 negatives for a net charge of +2. Now, when an atom loses electrons, the electrons that are lost are shown on the right side of the equation. The symbol we use for an electron is just E. We want to include its charge as well. So what is the charge of an electron? Now, a lot of times students want to do this. No, that is not right. That tells us that the charge of an electron is -2. That is not correct. The charge of an electron is -1. So how do we show in this equation that 2 electrons are being lost? We're going to use something called a coefficient. So let's put a 2 in front of the symbol for an electron. So magnesium, the neutral atom, forms a +2 ion by losing 2 electrons. Let's take a look at another example. So our next example, find chlorine on the periodic table. Question, how many protons and electrons does chlorine have? Chlorine has 17 protons and 17 electrons. Chlorine doesn't want 17 electrons. Any guesses how many electrons chlorine wants to have? That's right, chlorine wants to have 18 electrons. Like who? Like argon. So chlorine wants to be like argon. How can chlorine become like argon? Well, it needs to gain 1 electron. So this time, when an atom gains electrons, the electron or electrons that are gained are shown on the left side of the equation. So the neutral atom chlorine wants to gain 1 electron, and when it does so, it will form an ion that has how many protons? 17 protons. And how many electrons? 18 electrons. You have a particle that has 17 positives. Remember, each proton has a charge of +1. 17 positives, 18 negatives. Remember, each electron, -1 charge. For a net charge, then, of -1. Let's try one more. Find nitrogen on the periodic table. How many protons and electrons does nitrogen have? It has 7 protons and 7 electrons. Guess what? Does nitrogen want to have 7 electrons? No, it does not. How many does it want to have? Pause if you need to. Nitrogen wants to be like who? Nitrogen wants to be like neon. How many electrons does neon have? That many. So how can nitrogen become like neon? Remember, it's not going to turn into neon. It wants to become like neon. To do that, it needs to gain 3 electrons. So remember, when an atom gains electrons, those electrons that are gained are shown on the left side of the equation. If nitrogen gains 3 electrons, the ion that forms will have how many protons? Still nitrogen, 7. How many electrons? 10, like neon. 7 positives, and negatives for a net charge of -3. You can write -3 or 3 minus. Same thing up here. You can write +2 or 2 plus. Either way is perfectly fine. So I've already shown you one way of representing an atom using hyphen notation, like carbon 12, uranium 235. Another way of representing an atom is through something called a nuclear symbol. So here's how it works. You have some number Y over some other number Z next to some letter or letters X. So we'll start with X. That refers to the chemical symbol of the atom. That comes from the periodic table. The top number, Y, is the mass number. And remember, go back and review. Mass number is the number of things in an atom that have mass, simply the sum of the protons and neutrons. Where on the periodic table is mass number? Nowhere. So mass number needs to be given to you. Or at least you need to be given some information that will allow you to determine the mass number. The bottom number in the nuclear symbol, Z, refers to the atomic number. Where on the periodic table is the atomic number? That's right, it's that whole number above the symbol for each element on the periodic table. So that is the number of protons. That the top number in the nuclear symbol will be the bigger of the two numbers. The bottom number is smaller. So let's take a look at some examples. So we said there's 3 naturally occurring isotopes of carbon. We call them carbon 12, carbon 13, and carbon 14. Let's write the nuclear symbols for those 3 isotopes. Let's start with carbon 12. What number goes on top? Well, in the name, that 12 is the mass number. What number goes on the bottom? Well, it's carbon, so it has 6 protons. Its atomic number is 6. And the symbol from the periodic table is C. Go ahead and pause the video, write the symbol for carbon 13. So 13 is the mass number of that particular atom. So that goes on top. Bottom number for the nuclear symbol of carbon 13 is still 6, and it's still C. Pause and write the symbol for carbon 14. This time we have 14 over 6. I like to say it's not a fraction, but that'll help me if you're telling me the answers. 14 over 6, C, is the nuclear symbol for carbon 14. Go ahead and pause the video, write the nuclear symbols for both isotopes of uranium. You might need to go back in your notes and see what those are. Pause the video. All right, uranium has 2 isotopes. Here they are. So hopefully you found them. They are uranium-235 and uranium-238. Here are their nuclear symbols. Again, just another way of representing an isotope, or isotopes in this case. All right, so let's get back to that other number on the periodic table. I know in your notes it says atomic weight. I like to call that average atomic mass. So why is that a decimal number, that bottom number? Well, it's because it is an average. Now be careful, it's not a straight average. Example. Carbon has 3 isotopes, carbon 12, carbon 13, carbon 14. One has a mass of 12 AMU, one has a mass of 13 AMU, one has a mass of 14 AMU. Go ahead and pause the video and calculate the average mass of carbon. Don't look at the periodic table. So what is the average of 12, 13, and 14? That's 13. Now go to the periodic table. The average atomic mass of carbon should be 13. And it is not. Why not? Well, it's because average atomic mass is not a straight average. It's something called a weighted average. Not all of the atoms of carbon are equally represented, meaning you don't have the same number of carbon 12s as carbon 13s as carbon 14s. If you did, then sure, the average mass would be 13. So in any particular elements, the isotopes are present in different quantities, or something we call percent abundances. Here's an example. There are 2 naturally occurring isotopes of chlorine. One is chlorine-35 with an atomic mass of 34.9685 AMU and a percent abundance of 75.77%, meaning in any sample of chlorine, about 76% of them will have a mass of about 35. The other isotope is chlorine-37 with an atomic mass of 36.965980 AMU and a percent abundance of 24.23%, meaning in any sample of chlorine, about 24% have a mass of about 37. Calculate the average atomic mass of chlorine. Well, if you have some room at the top of the page, let me give you an equation that we use to calculate average atomic mass. Here's what it looks like. You take the mass of one of the isotopes, so I've just labeled that with a 1, times the percent abundance. I would change that percent to a decimal, by the way, plus the mass of a second isotope times its percent abundance, plus, keep going, as many isotopes as there are. Tin, for example, has 10 naturally occurring isotopes. You would do this 10 times, add all that up, and you get your answer. Notice, unlike a straight division, there's no division here. Sorry, unlike a straight average, there's no division. You don't divide. You don't add them up and then divide by however many. Percent abundance times mass plus percent abundance times mass plus percent abundance times mass equals. So let's go ahead and do this. Let's set it up. I'm going to have you calculate the answer because I want you to use your significant figures. So the mass of the first isotope, we'll take this one here. We're going to take that and multiply it by the percent abundance of that isotope. And again, I said, go ahead and take that percent and convert it to a decimal. You can do so by dividing by 100. So we get 0.7577. And do the same thing for the second isotope. The mass is 36.96590 EMU. And its percent abundance as a decimal, 0.2423. All right, notice again, here we go, mixed operations calculation. We're multiplying first and then we're adding. So my suggestion is do the multiplication, get this number and get this number, and then add them up using the rules for addition. Go ahead and do that, and when you're done, check your answer. Go ahead and pause the video. Did you get the right answer? Some of you are probably thinking, he said check. How am I going to check to see if I'm right? Well, remember, where can we find that number, the average atomic mass? It's on the periodic table. So did you get something close to that? 35.45, 35.46? That's what you should get. Again, we're going 2 decimal places because of that number. It's the least precise of those values that we are adding. All right, try the next one on your own. It says lead is composed of the following 4 isotopes. You have lead 204, lead 206, lead 207, lead 208. Those masses of each isotope and their percent abundances are given to you. Go ahead and apply what we just did with chlorine to lead and calculate the average atomic mass. When you get your answer, check to see if you're right. Go ahead and pause. Did you get 207 AMU? And again, be mindful of your sig figs. I think one of them we have our last digit in the ones place. So when we add up those 4 numbers, the last digit in our answer is going to be to the ones place. So we have no digits after the decimal. So we get 207 AMU. All right, since we've already gone over ionization equations, I'm going to have you do some on your own instead of me doing them for you. Let's start off with positive ions or cations. Remember, when atoms lose electrons, they form cations. So let me give you a couple. Go ahead and pause the video after I list these, and then we'll compare answers. So go ahead and write the ionization equations for potassium, scandium, aluminum, and barium. All of those elements are metals. They will all form cations. Go ahead and pause and do that now. Here's what I got. Did I get them all right? I sure hope so. Now, let me guess. Some of you probably show that aluminum wants to be like argon and can do so by gaining 5 electrons. Well, that's not the case. Aluminum is a metal, and metals always like to lose electrons to form cations. The closest noble gas to aluminum in number is not argon, it is neon. All right, let's try some anions. So again, let's write the ionization equation for elements that form anions. Remember, To form an anion, an atom has to gain one or more electrons. Let me list them for you, and then you can pause the video. We'll just do 3 this time. Go ahead and pause the video, write the ionization equations for each of these substances. I hope in these examples I don't see symbols like Ne and Kr. Again, it's not turning into a noble gas, just wants to be like a noble gas. So here are the results. That concludes this lesson, in fact, this unit. Please let me know if you have any questions. Thanks.